last bit in this, let's complete it. Put the heading SSB demodulation. SSB demodulation. Okay. So, if you take AC by 2, MT cos 2 pi FCT minus M hat T sin 2 pi FCT, or let's take plus, no, doesn't matter, right? Or you can also take minus plus, no problem. If you give this signal, to envelope detector, what will it do? If you give this signal to envelope detector, what will it do? It will take the coefficient and square it. It will become ACMT by 2 ka whole square. If you recall, A sin theta plus B cos theta. I taught you in one of the sessions. So it will give you root under A square plus B square. So similarly, we will get ACMT and ACM hat T by 2 ka whole square. Okay. That will be the envelope detector output. Okay. Now what I'm going to do, I'm going to take MT something, right? So let's take MT equal to cos 2 pi FMT. So the output of envelope detector will look like this. Output of ED, it will be root under AC square by 4, MT is cos, so cos square 2 pi FMT plus AC square by 4, and what is M hat T, guys? Cos M hat T is sin 2 pi FMT, so you get sin square 2 pi FMT. Clear? So you know that it will be root under AC square by 4 into 1, because cos square theta plus sin square theta is 1. Root of AC square by 4 is AC by 2. This is not masses, right? This is not empty. This is just half of the amplitude of the carrier. So you can clearly see that doesn't matter what message you are sending, your output of envelope detector is always constant, which is equal to AC by 2. Okay. So we know that when we applied amplitude modulation to the envelope detector, we got the envelope and we were able to do it given the condition that mu is less than 1. But when we gave double sideband suppressed carrier to the envelope detector, we got mod of MT. Remember that? And here, when we gave SSB to the envelope detector, we get constant. These things can be asked as a match the following question. So let me do the summary here. So guys, come back. AM signal. So if you had AM signal something like this, we have done so many times that we are too good in this, right? In drawing and all. So this is your AM signal and it goes into the envelope detector. What is the output you got? The output you got was this. Means your empty. This is empty. So this is nice. Putting a tick mark. Now if we take DSP signal, which is like this, and again you give to the envelope detector, what is the output you got? The output you got was this, if you recall. So this is mod of MT. So we don't want that, right? And the last thing we did, if we give SSB signal to the envelope detector, what is the output you got? A constant line. AC by 2. See? So guys, the conclusion is that envelope detector we can only use for aim, and that too for mu less than 1. For other demodulation technique, for single sideband and double sideband, we have to use synchronous detector. So envelope detector can be used only for aim signal, that too for mu less than 1. If it is not less than 1, we can't use it. You can see that. DSB, we can't use it. Single sideband, we can't use it. So write this note. This is very, very important point. Envelope detector demodulation technique. Envelope detector is used to demodulate only aim signal, and that too mu has to be less than 1. For double sideband suppressed carrier and SSB signal, we use synchronous detector. We use synchronous detector. Now put the heading synchronous detector. Synchronous detector. So guys, you have a SSB as input. You take a multiplier and multiply carrier signal generated by local oscillator at the receiver's end. Okay? So guys, this is just like a balanced modulator, or simply you can call it as modulator. Why I'm saying modulator? It's a demodulator, or you can simply call it a multiplier. Okay, not modulator, multiplier. It multiplies. Okay, and the output will go into a low pass filter. Okay, so we have this signal AC by 2 MT cos 2 pi FCT minus plus M hat T sin 2 pi FCT, and you are multiplying this with the carrier AC cos 2 pi FCT. So you are multiplying the whole thing with AC cos 2 pi FCT. So what do we get, guys? We will get AC square by 2 MT cos square 2 pi FCT minus plus M hat T AC square by 2, and you get sine into cos, so multiply 2, so it will become divided by 2, 4, it will become sine 4 pi FCT. So if you go one step further, you will write AC square by 2 MT 1 plus cos 4 pi FCT, and divide by 2 will become 4 minus plus M hat T AC square by 4 sine 4 pi FCT. So we well know that this will give us 2 FC frequency, this will also give us 2 FC frequency. So this is like 1, but output of low pass filter will do what? They will cancel this and this, it is gone. you'll only get AC square by 4 times MT. So first, we need to understand what is the problem with synchronous detector. That we already know there is a challenge of phase shift. So let's quickly finish this. Problem with synchronous detector. Okay. You know, if there is a phase shift, then it will create a problem. So just write that when the carrier signal generated from local oscillator has a phase shift of phi. So what will be the output of the low pass filter now? So the output of LPF will be equal to, now guys, I am writing this directly, AC square by 4 MT cos phi, okay, minus plus AC square by 4 M hat T sin phi. Please remember this, don't ask for proof and all, it is little lengthy, okay. AC square by 4 MT cos phi. You want to do the proof, you can do, but don't ask me. Just keep in mind. If phi is equal to 0, then again it will come to AC square by 4 MT. You can see that. But if phi is equal to 90 degree, then what you will get? You will get minus plus AC square by 4 M hat T. So rather than receiving the masses signal, you got the Hilbert transform of that. Look at that. So guys, unlike DSB and AM, we don't have quadrature null effect. Here, no quadrature null effect, because in all the time we have the output. No quadrature null effect. No quadrature null effect in this. No quadrature null effect. Okay. So this is all about synchronous detection of SSB and what is the challenge. Now there is a problem with, right? There is a problem with SSB itself. So put the heading problem with SSB. Now we need to understand when you did this double sideband, you had something like this, correct guys? Remember that? So this is WC, WC plus W, and this is WC minus W. This is minus WC plus W, minus WC minus W. This is your double sideband suppressed carrier. Okay? Now, if you look at this, and you are thinking to have an ideal band pass filter, then everything looks very good. But generally, we don't have an ideal band pass filter. We have a practical band pass filter, which will be something like this. Right? So if you look at this, so this band pass filter will not only get you, similarly you can have here as well. Oh, sorry, my bad. Yeah. Now, if you expect that you will only get upper sideband, that's your illusion. What will happen? That you will get something like this. You will also get some extra part from here, and I would say that you will get something like this. So you are supposed to get this, Okay, you're supposed to get this. Let's say you have, yeah. So you're supposed to get this, but you got this as extra. Are you feeling, guys, what I'm trying to say? Guys, are you there? You will get this extra. So this is not only upper sideband, this is upper sideband plus some traces of lower sideband as well. Please write. And the band pass filter you are looking at is not ideal. So guys, ideal band pass filter is a myth. It doesn't work. It doesn't happen. Okay. So to solve this problem, we use only certain type of signal, and that is voice signal. So write that as a note. SSB modulation technique. SSB modulation technique is suitable for transmission of voice signal only. Voice signals only. So what is the spectrum of voice signal? Let me show you. I drew this in the first session as well. So what is spectrum of voice signal? It looks like this. So you are having from 300 Hz to 3500 Hz, and similarly we'll have the mirror image as well. So minus 300 to minus 3500 Hz. Frequency is in Hz, right? Even if you shift this, yes. So let me shift this. So even if you shift this, you'll get something like this, correct? Something like this. Right? Let's say this is your double sideband suppressed carrier for DSP, and for the voice signal, right? So it is your omega C, but it is starting at omega C plus 300, and this is like omega C minus 300. You actually get a guard band of 600 Hz. There is a guard band of 600 Hz. Now, even if you deploy a practical band pass filter, right, you can think something of this, right? So you can think of practical band pass filter something like this. Still, you can see that your peak is coming here and your peak is coming here. So you will get proper this part, upper sideband. Look at the beauty. So I'm only doing for positive frequencies. So what is the need of the signal is there should be a gap of certain frequencies, so that practical band pass filter attenuation thing is not picking it something else. Are you getting my point, guys? Why SSB modulation cannot be used for any general signal? It has to be used for a signal which is not having significant low frequency component here. So that is something we should write now, guys. And if there is nothing at the 0, f equal to 0, it will have some guard band when it is going into DSP. So write that as a very important point. Please write it down. In the case of voice transmission, In the case of voice transmission, a spectral gap of 600 Hz exists between lower sideband and upper sideband, which you just saw, right guys? Continue. So it's possible to eliminate one sideband completely. One sideband completely, even though filter is not having sharp cutoff frequency. Even though filter is not having sharp cutoff frequency. Sharp cutoff frequency. Guys, with this, we are done with complete SSP.